We are ready to talk about natural and step response. So we have the natural response and we have the step response. Now, this is what they're called, but let me try to explain sort of what they are. If we were talking about just, let's say, capacitors. Capacitors charge up or they discharge. So you have charging and you have discharging when it comes to capacitors. So a natural response for a capacitor would be discharging behavior. So the discharging behavior would be the natural response for an RC circuit. So if I'm going to combine a resistor and capacitor together in a circuit, the capacitor, let's say, already has some charge on it before I flip the switch and this circuit starts doing whatever this circuit does. Then as it discharges, we're going to call that the natural response. Okay, it's just the natural response of a discharging capacitor. Okay, however, if we're charging it up, the charging behavior for an RC circuit would be called the step response. Now, that kind of makes sense when you're talking about RC circuits, but when you're talking about RL circuits, where we have a resistor and an inductor together, you don't really talk about charging and discharging. And that's because, well, it makes sense when you're talking about capacitors, but it doesn't make sense when you're talking about inductors. So what's really going on in the case where you're discharging the capacitor is that we have energy that is decay. So we have a decaying energy. So energy is being lost from the system. So in other words, if there's charge on the capacitor and then you throw the switch and the capacitor begins to create a current, well, if that current goes through the resistor, you know that the resistor is going to dissipate away energy at a rate of I squared R. And that's going to cause the energy to decay. Okay, unless you get the energy from somewhere else, which in this case we wouldn't, because we're talking about the natural response and solely discharging behavior, the energy is going to dissipate away. So we're talking about decaying energy. However, when we're talking about the step response, we're charging the capacitor. We're also increasing the energy that's in the magnetic field for the inductor. So this is going to be energy rise. So we have energy decaying and energy rising. That's really the difference between the natural response and the step response. Now, as we go through these two responses here, here's what you're going to discover. You're going to discover that the solutions for all of these are all first order ordinary differential equations. Okay? Now, that's kind of important to us. That's useful because that means that these solutions can be reduced down to Thevenin equivalents or Norton equivalents. So a VTH and RTH are going to show up here. And that'll make more sense, I think, when we get to that point, but I'm just kind of giving you a heads up. Natural and step responses for RL and RC circuits are going to be first order differential equations as their solutions, which are naturally going to lead to us being able to do Thevenin and Norton equivalent circuits here. Okay, so let's go ahead and get started. And here's the way I'm going to set this up. Let's say that I have a circuit that has a current source, a resistor in parallel to it. Let's call that current source I sub S. This resistor R naught. And this is connected through a switch to an inductor. They share ground and a resistor. Also, we'll draw it like this. So here's our resistor, here's our inductor, and let's say the switch is originally closed but is now going to be opened. Okay, so before t equals 0, that switch is closed, and it's been closed for a long time. So what's going to happen here? Well, if you'll think about the current from the current source is going to come along here, and some of that current could go through the resistor, some of it could go through this resistor, some of it could also go up through the inductor. Now, originally, when that current first starts to flow, the inductor is going to create a back EMF. Remember, it's going from having no current going through it to having some current going through it. So rather than it occurring instantaneously, it's going to generate a voltage that's related to di dt. And that voltage is going to oppose the current, so that initially zero current is going to go through that. Another way to think about that is you cannot have an instantaneous change in current for this inductor. And what this current's coming along here, it's trying to go through the inductor, but the inductor is going to oppose that so that the current doesn't change too quickly. Okay, but after a long time, remember that switch is closed, and it's been closed for a long time, eventually the current wins and the inductor is going to build a magnetic field inside its coils, and it's going to contain a certain amount of energy. But after a long time, that inductor behaves just like a piece of wire. So any current that's coming along here is just going to pass right on through the inductor pretty much unhindered. So that's the situation that we've got at t equals 0. So how much current is going through the inductor? Well, if that's just a piece of wire, then all of it. There's essentially a short circuit across this current source here, where the current can come down here. And think about what the current's choices are here. Current could either go up this way, or it could go down here. It could go this way, or it could go up that way. Well, the current is always going to pick the path of the least resistance. So in this case, after a long time, this is just a piece of wire here. So all of the current's going to go through that. So right at t equals 0, because the switch has been closed for a long time, right at t equals 0, all of that current, all of I sub s, is going through the inductor. And that's the situation again, right at t equals 0. Okay, so now we've got all of the current going through that, but now the switch is open. And when the switch is opened, the left portion of this circuit pretty much is no longer there as far as we're concerned. So after t equals 0, this is what we've got. We've got our inductor, we've got our resistor. And the initial current here, so that current, the current going through the inductor. Now there's really only going to be one current for this loop after t equals 0. I'll call it I sub L. So I sub L evaluated at 0, so right at t equals 0, is I sub S. Okay, that kind of makes sense then, doesn't it? Okay, you cannot have an instantaneous change in current, so even after the switch is opened up, you're still going to have the same current I sub S going through that inductor after t equals 0. Okay. All right, well, now that we've done that, we could say this. Well, the voltage across the inductor plus the voltage across the resistor has to equal 0. That's nothing but KVL around this loop here. So those two voltages have to add together to be 0. Okay, well, what's the voltage across the inductor? The voltage across the inductor is L di dt. Plus, okay, what's the voltage across the resistor? That's just I times R, and that has to equal 0. Okay, this right here, this is the first order differential equation. That's the equation of state for this circuit right here. And you notice we've only got one variable here, it's I, and we should be able to find I as a function of time. All right, this is pretty simple, pretty straightforward to solve this kind of differential equation. You do it by separation of variables. So let's just go through the steps. Let's say L di dt is going to be equal to minus I R. Let's put the dt over here. So we'll take the dt, move it over here. We'll take this I, we'll put it over here. It's going to be like a 1 over I here. Let's take the L and put it over here. So it's going to be like that. And now let's rewrite this. 1 over I di is equal to minus R over L dt. Okay, so we've successfully separated the variables here. The R and the L are constants. The I is going to be a function of time. So if I integrate both sides of this, I need to integrate that. I'll need to integrate this dt as well. But we need to start at some initial time, and that initial time is going to be when that switch is open. Now, in general, you would call that t naught, but we know for our specific case that it starts at t equals 0, and then it goes to some arbitrary time t in the future. Over here, this I, we're integrating over I, so this is going to be I at this first time, so I at 0. And then the top limit is just going to be I at some arbitrary time t later. Okay, so right-hand side is pretty straightforward. We're going to have minus R over L, and this is just going to evaluate to be t. It's really t minus that initial time, but it's 0 in our case. Left-hand side, you recognize this as just a natural log. So it's the natural log of I, and we need to evaluate that from I at our starting time to I at our ending time. Okay, let's plug in for these. This is going to be the natural log of I t minus the natural log I 0, and that's equal to minus R over L times t. You notice we have a difference in natural logs. There's a rule that says you can write this as a quotient, so we can write this as natural log of I of t divided by I of 0, and that's equal to minus R over L times t. All right, now we're after I as a function of time, so that's what we want to solve for right there. We need to get rid of this natural log then. You do that by taking an exponential of both sides here, and we end up with left-hand side just being I of t over I of 0, and that's equal to e to the negative R over L times t. Okay, multiply through by I of 0, and we end up with I of t is going to equal I of 0 e to the negative R over L times t. And that is what the current is going to look like for t greater than 0. Okay? Now, this exponent here is, you can see it's a decaying exponential, so if I were going to graph this, I versus time, it's going to start at some maximum value here, and that maximum value is going to be I at 0, and then it's going to decay over time, and it's going to eventually reach 0 in the limit here. Okay, at t equals infinity, it's going to be that. Let me ask you a couple other questions about that. That's what I is, all right? That's the current through the inductor as a function of time. That I of 0 is this I sub s. So I could rewrite that current I as a function of time is equal to I sub s e to the negative t over tau. And now I just made a substitution. I let tau, we're going to call that the time constant, and it's related to how quickly this decay occurs. So it's really a factor that controls the rate at which the decay occurs, whether it happens quickly or slowly. And we're going to define tau as L over R. So this becomes T over tau. And that'll be useful to us, especially when we get to capacitors, doing the same sort of thing with capacitors, that a tau is going to pop up. This specifically is the inductive time constant, so I could put a subscript L on there, although I often forget to do that. You could do that. All right, now the couple of questions. What about the resistor in our circuit here? This resistor R. What is the voltage across that resistor as a function of time? Well, the voltage across the resistor, we've already said, is I times R. So I could solve for that. Voltage across the resistor is just going to be I as a function of time times R. So the I is given by that, so it's going to be I sub s times R e to the negative t over tau, like that. So you'll notice here what we've got. This looks an awful lot like Ohm's law, where V equals I times R, except it's got this time component on it here. And that time component is causing the voltage to decay over time. And if you'll think about what's going on here, after the switch is opened and the right-hand portion of the circuit is isolated from the left-hand portion, the current I sub L is going to start flowing as the magnetic field in the inductor decays. But as the current passes through the resistor is going to heat up and it's going to dissipate away energy in the form of radiation that is going to be dissipated at a rate of I squared R. So that's the energy that's leaving the system. So energy that's leaving the system is what's causing this decay to occur for the current, and it's what's also causing the voltage to vary over time. So the voltage across that resistor looks like Ohm's law, but with the time portion in there as well. This doesn't apply. This is the correct answer there. Okay, so what about the inductor? Let's go back here. Well, the inductor has this as its voltage. V sub L is L di dt. So the voltage at any time for the inductor is going to be given by L di dt. Now, before we do that, think about what you expect it to look like, even before you start looking at the math. What do you expect to happen to the voltage across this? We know that this voltage plus that voltage added together has to be 0, okay? So you expect something to be going on there so that ultimately, after a long period of time and all the energy is radiated away, don't you expect this one to decay as well? So this is going to decay and that's going to decay. So they're both going to go to 0 after a long time. Okay, but let's see if that works. V sub L is L di dt, so it's going to be L and the derivative of this. Okay, well, what's the derivative of that? Let's see, there's I sub s times negative 1 over tau sub L times e to the negative t over tau sub L. Okay, well, tau sub L is this L over R, so this is going to be minus L I sub s. I brought the minus sign out front. Now this is 1 over tau, so it's going to be R over L e to the negative t over tau. And you'll notice the L's will cancel here, so this is going to be minus I sub s R e to the negative t over tau. Look at that. The voltage across the inductor, V sub L, is the same as the voltage across the resistor. The only difference is that sign. Now, you should have expected that because these two things have to add up to be 0. So one of them had to be negative in order to make that happen. And because they're changing over time, as this one changes over time, you expect this one to change over time at the same rate so that when you add them together, it has to be 0. And we see that here. So in other words, as the resistor dissipates away energy, its voltage decays, and the inductor's voltage decays at the same rate, except its voltage is negative, and that's so that the two voltages, when added together, equals 0. Okay. All right. Well, let's see what else we can tie in here. What about the power? What is the power dissipated by the resistor? In other words, power is going to be I times V, or in the case of a resistor, we could say I squared R, or even V squared over R. Any one of those should give us the same answer. We could use any of these to make a substitution. So this is the power, the rate at which energy is dissipated away by the resistor. So let's see. Let's take this one right here. Let's do V squared over R. So this is going to be, this one is going to be I sub S R e to the negative t over tau. Now we need to square that and then multiply by 1 over r. Okay, so what do we end up with? I sub s squared times r, one of those r's cancels here, times e to the negative, and this is going to be 2t over tau. Okay, look at this now. This is going to look the same sort of way. This is P equals I squared R. You know, for Ohm's law, if we only had resistors, P is going to be I squared R. But now we've added on this time component, and it's not exactly the same time component that we had up here, because it's negative 2t over tau. All right, so it looks like this is going to decay at a different rate than this up here. Okay. Nevertheless, you can see the parallels here. It's very similar to what we had when we were looking at only resistor type circuits. Okay, what about energy? What is the energy that's being supplied to the resistor, let's say? Well, again, P equals dW dt. That's actually our definition of power. It's energy per time. So you could solve, we could go through the steps of this if we want to. You're going to end up with dW equals P dt. Now integrate both sides of this. You're integrating from t equals 0 to some energy W later, and this is going from 0 to that arbitrary time t in the future. So this is just going to be W on the left-hand side. That's total energy. And on the right-hand side, we're going to end up with the integral from 0 to t of this right here. I sub s squared r e to the negative 2t over tau dt. Let's see, the I sub s squared and the r are constants, so we could factor those out. And really we're just integrating this e to the negative 2t over tau. Now you go through the steps. I'll leave it up to you to show that this is the case, but you're going to end up with the energy equals 1/2 L I naught squared, I'm sorry, that's I sub s squared, times 1 minus e to the negative 2t over tau. And that is for t greater than 0. So here we have an energy relationship here. Now, you'll notice it looks a little different here. Rather than it being a decaying, it's a 1 minus e to the negative t over tau. That's because of the way that that I worded this question. This is the energy that's being supplied to the resistor. So the energy is coming from the inductor. Remember, at t equals 0, all the energy is in the magnetic field inside the inductor. But over time, that energy is being relayed over here to the resistor. And over time, over the entire amount of time, from 0 to whatever arbitrary time t, you can see that it's dissipating away that energy. So the resistor dissipates away energy at the same rate that it is supplied. If that were not the case, the resistor would either explode or not do anything. It has to dissipate away energy at the same rate that it's received. So if you were to graph the energy versus time, then over time it gets all of the energy. So this is a summation of the energy. So at any specific time t, you could look and see what that energy is, but after a long time, after a significant amount of time, then all of the energy is given. And what is that energy? That's just 1/2 Li sub s squared. So that looks an awful lot like an equation that we saw earlier in the class, 1/2 Li squared, but we've got this sort of rising and leveling off exponential here, because that's the total energy that's being supplied to the resistor at any point. Okay. Let me summarize sort of everything we've talked about here when it comes to this inductor. You notice that this e to the negative t over tau appears quite often. And I said tau is L over R. So when we were talking about the voltage, when we talking about current, when we talking about all of these things, even the power, there was a similar type thing. It's 2t over tau, or 1 minus e to the negative 2t over tau. Those show up quite often. So keep that in mind here. There's a little bit of a pattern. You can recognize that. The current, I of t, was whatever that initial current is times e to the negative t over tau. The voltage, as a function of time, was whatever that initial, let's call that, I called it I sub s previously. We'll keep that notation. I sub s times r, e to the negative t over tau. And the power, as a function of time, was I sub s squared r, e to the negative 2t over tau. And the energy that's being supplied or dissipated away, either one, is 1/2 L I sub s squared times 1 minus e to the negative 2t over tau, like that. Okay? So these set of equations here represent the natural response for an RL circuit. Okay? Now, let me talk about this thing that keeps popping up, the e to the negative t over tau. If you create a chart here of time versus e to the negative t over tau, like that, here's what you find out. That tau is actually a unit of time. Remember, tau is L over R, but if you look at the units and you trace it back to its fundamental components, like you would in a physics class, here's what you discover. You discover that tau fundamentally has units of seconds. So it is a time. And you'll see here the exponential. Remember me saying previously that the exponential doesn't have units associated with it. Well, the reason is because the units cancel out. The t is units of seconds. The tau is also units of seconds. So this exponential thing here doesn't have any units attached to it. So you can talk about tau as if it is a time. And it is. So you could say after 1 tau of time, you plug that in here. Do this with your calculator. To t, plug in 1 tau for t. The t's means the taus are going to cancel, and I'm going to be left with e to the negative 1. Okay. Well, e to the negative 1, when you plug that in, is 0.36788. Okay. So that's 0.36. So about 0.37, so 37%. Remember us drawing this right up front. So after 1 tau of time, and we could just say that that's 1 tau there, then this thing has dropped down to 37% of whatever its maximum was. So it's reduced significantly after 1 tau of time. After 2 taus, then that's going to be e to the negative 2. That turns out, if you plug that into your calculator, to be 0.13534. So in other words, about 14%. So now it's dropped down to 14% of what it was originally. It turns out to be 0.049787. Okay, so that's about 5%. So after 3 tau of time, it's done 5% of whatever it's going to do. So if it's decaying, it's 5% of what it was originally. After 4 tau of time, the trend continues so that it is 0.018316. So 2%. It's down to 2% of what it was originally. 5 tau of time, it is 0.00673779. So now we're right at, rounding 1%. So after 5 tau of time, it's at 1%. Now, if we continue this on, 6 tau, e to the negative 6, well, that turns out to be 0.00247888. So it keeps getting smaller and smaller. Now we're less than 1%. We're down into very small numbers. You could continue this trend on. What you would discover is that no matter how far you go in time, in counting taus, you never really get to 0. And that's because of the nature of the decaying exponential. If you recall, I said it reaches 0 in the limit. So as t goes to infinity is when because of that decaying exponential, reduces down to 0. So the question becomes for an engineer, when is this thing finished? When is this circuit done, whatever it's going to do? If it's a decaying exponential that obeys these rules here, these equations here, then when is it done? And the traditional answer is after 5 tau. So after 5 tau, we are getting down below 1%. And we'll say that this thing is effectively done. So somebody says, how long is a long time? A long time is 5 tau, because after 5 tau of time, this thing's finished doing whatever it's going to do. Okay? Now, given all of that, we have just seen that there is a transient response. So the transient response for a natural response occurs for t less than 5 tau of time. But after 5 tau of time, then we are in the region of what is called the steady state. So it doesn't change much after that. And this occurs at t greater than 5 tau. Okay? It's just something to think about. As we go farther into the class, then it'll be a little easier to see what that means, especially when we start talking about steady state responses to AC circuits. So let's say that now you have an RC circuit. An RL circuit. Let's say that you have an RL circuit and you need to solve it. Well, the only type of circuit that you can solve at this point is one where you have an inductor and a resistor. So you've got an inductor and you've got a resistor here. Now there's some initial current going on here, so there's some I at 0. You know that there's going to be a time constant, that's the tau. So you need to figure out what the tau is. And then you could solve for any of these top 2 components here. So look here. The current is just going to be whatever the maximum current was at the beginning, multiplying by that. The voltage is going to be whatever the maximum voltage was, that's I times R, or that's the maximum voltage, times the decaying exponential there. So if you want to solve this kind of circuit, here's what you need to do. Use your circuits knowledge to figure out what the initial current is at t equals 0. Calculate what tau is. And then just plug it in to this equation that says it's going to be whatever that is, e to the negative t over tau. There's your answer. That is the current equation in units of amps. This I sub s, that is what I called I0 right there. In other words, it's the initial or the maximum current. And you know that over time, if we were to plot it, it starts off at that maximum value and it decays over time into 0 in the limit. All right. Let's see. We could probably do one more problem here. I think it'll go relatively quickly. Let's say that we've got this circuit. Now there's a switch here. The switch is originally closed, so the switch is opened at t equals 0. And what we want to find is the voltage, V0, across that 60 ohm resistor there. Okay, now in order to do this, you need to follow those pretty straightforward rules that I just told you about. Figure out what the initial current is, figure out what tau is, and write the equation down, and then you're done. Well, in order to do that, you have to think through, using your circuits knowledge, what's going on here before t equals 0, so that you can figure out what that current is through the inductor. Before t equals 0, the switch has been closed for a long time, so any current that's coming along here is going to treat this inductor as if it is a piece of wire. There's energy stored in the inductor through inside the magnetic field, but current, after a long time, is just passing through it like it's a piece of wire. So if that's the case, then any current that's coming along here, either down or going up, doesn't matter, is going to pass through here and not allow any of that current to go over here to the right-hand side of the circuit. So this part over here may as well not even be here before t equals 0, because no energy is going in that direction. All of the current, all the energy is just passing through that inductor. So if that's the case, then before t equals 0, this circuit could be redrawn as, the inductor would be right here, but you know, it's not there. It's just acting like a piece of wire. So let's say that that's the current going right there. There could be another current right here, and current coming out of this 80 volt source. Okay, so we could imagine the currents going in those directions right there. If we do that, then you can see that this is a current divider. Let's call this I sub s, I from the source. This is going to be I sub L. That's the current going through the inductor. And let's just say this is I2. All right. Well, I sub s is pretty easy to figure out if you realize you got these two 50s in parallel here. And that parallel combination is in series with that 15. So what do we got? We got a 50 that's in parallel with a 50 plus a 15. Now the 50 in parallel with 50, that's going to give you a 25. And the 25 plus the 15 is going to be 40. So this is a 40. So this whole thing right here is a 40 ohm equivalent resistance then. So I sub s is going to be I V over R, so that's 80 volts over 40 ohms, so it's going to be 2 amps. That's what I sub s is. And that I sub s then is going to be split down these two paths right here. Now, notice that those two branches after this essential node right here, I sub s is split in those two branches, and they have equivalent resistances, so that means that I sub s is going to be split equally. So I sub L is going to be 1 amp. I sub 2 is also going to be 1 amp, so we could say I2 as well, also 1 amp. Now, the reason we did that is because that's what the current is going to be through our inductor at t equals 0, because the switch is closed a long time before t equals 0, and I sub L is a steady 1 amp right there. So let's write that down this way. We'll say that I sub L at 0 minus is 1 amp. Now 0 minus, that's a way to say on the negative side of 0 as you approach the limit of 0, as you approach 0. Okay, so as t goes to 0 from the negative side, it's 1 amp. But it's also going to be I sub L at 0 plus. So on the positive side of 0, it's also going to be 1 amp. Now the reason for that is because you cannot have an instantaneous change in current for an inductor. So if the current is 1 amp right before t equals 0, it's going to be 1 amp right instantaneously after t equals 0. So what is that? That's our initial current through our inductor right there. Okay. Then at t equals 0, switch is opened, and the whole left-hand portion of the circuit might as well not even be there. So the circuit now reduces down to this. Okay, and we know what our initial current is through our inductor there. So this is I sub L, and that's going to change over time, so it's a function of time. All right, well, to find that voltage right there, we need to, well, we can combine this 60 and the 20. We know that those two are in parallel, so the 20 hanging out here is just kind of, distracting. So we can reduce this down to a 3, whatever that equivalent is, and the 2 down here. So there's the 2 ohm, here's the 3 ohm, that's our 0.2 Henry. And what is this? This is going to be 60 and 20, so that's going to be 60 times 20 over 60 plus 20. And do that math, that's going to be 15 ohms. So this is a 15 ohm, and that's our V naught right there. Okay. Now that I know what V naught is, look, it's going to be real easy at this point to figure out what tau is. Remember previously I said you can really only solve a circuit if it's got one inductor and one resistor, but you can think about this as being equivalent to that. There's our 0.2 Henry inductor. Well, what is this? Well, now you can see this is a 15 plus a 3 plus a 2, so this is going to be 20 ohms, and our inductor is 0.2. So tau, which is L over R, is going to be L 0.2 Henry divided by R, which is 20 ohms. Do that and you end up with 0.01, and the unit's going to be seconds here. Okay, so given this, we can now say that this current I sub L as a function of time is going to be 1 times E to the negative, now it's T over tau, so 1 over tau, since this is 1/100th, then 1 over that is going to be 100. So 100 T. amps. So there's our I. That's the current that is flowing here. That's also the current that's going here, and will also be the current that goes up through that guy right there. All right, so what is V naught? V naught is going to be, now notice the current is going in through the negative terminal of this 15 ohm. So we need to write V equals minus I as a function of time times R, and R is going to be 15. So this V naught is equal to negative this 1, I don't know why I'm writing the 1, but e to the negative 100t times 15. So V naught is equal to negative 15 e to the negative 100t. There's our answer for the voltage across this 60 ohm resistor, e to the negative 1500t. So it's going to start out at 15 volts, and the units are going to be volts here. It's going to start out at 15 volts, negative 15 volts, and over time it's going to decay. So if we were to graph that, this is V versus T, starting out down here at negative 15 volts, and over time it decays to 0 in the limit, like that. We'll stop here and pick up with RC natural responses next time.